Hey folks, welcome to episode 3 of Sound Decisions, and in this case it's also part 3 of the interview with Rob Watts. Now before I get into the content and what Rob's going to talk about, I just want to say a big congratulations to Marcel, one of the Passion for Sound patrons, who has been lucky enough to win the Mastrop Aorist R2R DAC. That's on its way to him, and Marcel, I hope you enjoyed the DAC as much as I did. If you'd like to win some gear of your own, just check out the link below to the Patreon page. Now in this part of the interview with Rob Watts, we get very technical and start talking about interpolation filters, or in Rob's case the WTA filters that he's designed for his Chord Electronics DACs. And he talks about what the filters do, the different approach that he takes, and how it compares to other manufacturers and even MQA in terms of reconstructing the audio signal. For much of this video, I've got images and slides on screen just to try to help the explanation, and as usual, I'll chime in from time to time to provide some extra clarity if I can. I guess what makes sense now is to talk about the WTA filters. And the WTA filter is essentially an interpolation filter, is that correct?
Yes, that's correct.
Okay, good.
Well, what it's trying to do is to reconstruct what's happening from one sample to the next sample. So it's not reconstructing, it's not changing the original samples.
Okay.
The intent isn't to try to change the original samples, but to calculate what's going on from one point to the next point.
Yep.
The difficulty we have here is that interpolation filters are not very good at reconstructing the bits in between. And we know from theory that we can perfectly reconstruct the original bandwidth limited signal if we use a sinc function. Now, a sinc function requires an infinite amount of processing, so we can't use sinc functions in reality. Now, the reason why it's important to reconstruct the waveform from one point to the next point is about transients.
Yep.
Transients are very, very important from a psychoacoustics perception point of view, because the brain uses transients in a number of different ways. So we use transients to locate instruments from left to right, and that's through the interaural delay. And this is a chain of neurons connected from the left ear to the right ear. And if the transient hits the neuron from the left side and the right side at the same time, the neuron will fire. And each neuron from the next one to the first one to the next one is between 4 microseconds worth of resolution. So you can resolve the timing differences between the left ear and the right ear to between 4 and 6 microseconds. And that's used as one of the cues to determine where the sound is coming from, from left to right. So placement information or transients are very important from that point of view. The other issue that we have is the ear is, as a bass transducer, is pretty poor, and it's got a lot of attenuation for low frequencies. It doesn't have many hairs that are triggered to reproduce pitch. It's not like 1 kilohertz where you've got 1,000 hairs to cover that, so you can perceive one hertz of pitch.
The hairs that Rob is talking about here is actually the way that our body senses audio waves. Basically, the way that it works is that sounds reach the eardrum, they're then carried through a series of 3 bones into the inner ear, and from there the vibrations created by the sound wave are sent through the inner ear, where there are tiny little hairs, a little bit like microscopic versions of the hairs in your nose, for instance. And what those hairs do is they vibrate, and different hairs will vibrate for different frequencies. And what Rob's referring to here is that we have different numbers of hairs depending on the frequency, and that's specifically from a biological survival point of view. There were certain frequencies that were more important. So for instance, the range of, say, the 1 kilohertz to 4 kilohertz in particular is very important. Those are frequencies that are important for our communication, and also the higher frequencies tend to be more important for us to locate sounds in the world around us. What Rob's saying here is that the bass frequencies are fairly inaccurate. We're good enough at picking up bass that we know it's there, but we're not very good at understanding the detail and the clarity and the quality of the bass without the transient information which comes in at higher frequencies, as Rob's talking about. The final part of us being able to hear bass effectively is that our ears are just mechanically not as good at carrying bass signals through into the inner ear as they are with high frequencies. So all of that combines to affect the way we hear bass compared to the way we hear high frequencies. And that speaks to why headphones are tuned so that they're not actually dead flat. They're tuned so that we are reproducing sound that accommodates the sensitivities of our ears. And that's why things like the Harman target curve for headphone design or headphone tuning has come about to reflect the way that we actually perceive in our sensitivity to audio. But that's a little bit of a different conversation. So for now, I'll hand it back over to Rob to talk about how the brain actually manages to use transients to identify the detail within the bass and what that means for his DAC design.
So what the brain does is that it uses the transient information, looks at the higher order harmonics, and then calculates it down from the higher order harmonics to what the low frequency pitch actually is. And they've done psychoacoustic tests where they've removed the transient information of a bass guitar, for example, and then it becomes very difficult to follow the tune of your bass guitar when you remove the transients. So transients are very important for bass pitch. They're also important for timbre perception. And again, similar psychoacoustic tests remove the transient information of instruments, for example, a piano and a trumpet. If you remove the transient information, it becomes very difficult to tell the difference in sound between the sound of a piano and the sound of a trumpet. That's pretty amazing because you can clearly hear a huge difference between the sound of a piano and the sound of a trumpet. So transient information are very important from a timbre point of view. I recognized this going back to the 1980s because when I was at university studying electronics as a science, my psychology lab was very close to my digs. And so in the weekends, I'd go into the psychology library and look up about the psychoacoustics of hearing. At that stage, I was very much an audio enthusiast, but I wanted to be an audio designer. And I thought if I understood how hearing worked, then I'd be a better designer. So that was the reason why I looked at it. And all this business about transients being important from a psychoacoustic point of view, from a perception point of view, was very clear from the textbooks. Also at that time, we were studying sampling theory, Shannon sampling theory. And you could see quite clearly that to reconstruct your unsampled, the original signal in the A to D converter, you needed to use a Sinc function. And that's how sampling theory is proven.
Now, Sinc functions get really confusing for me, if I'm being honest. The research I've done is very technical, very mathematical. And so to boil it down, my understanding is that the term Sinc function is really just a mathematical function to understand how the DAC responds to a single pulse. So if you send in a single pulse, what will actually happen with the Sinc function is that you get the main sound wave output of the DAC, but on either side of the main pulse, before it and after it, you get a rippling effect of what's called pre-ringing and post-ringing. Now, this is getting into a territory that I really don't fully understand, but the gist of it that Rob's about to explain is that if you're using a Sinc function as part of your filtering process, the filters are able to take that pre-ringing and use it to extrapolate what the signal should have actually been. So by looking at it over and over and over again, and this is the idea of taps, so with 48,000 taps, what Rob's saying is that they're able to basically recalculate or revisit the filter 48,000 times to use that rippling effect to calculate what the different frequencies at any point in time should actually be. So again, that's a very simplified version. I'm sure engineers out there are probably cringing at the way I'm trying to simplify this, but it's the best I can do to explain it for people like me who are not of an engineering mind, but do want to understand how Rob's approach to filtering works and how it's different to other filters. So in other filters, as Rob's going to go on to explain in a bit of a more technical way, other filters are actually not using this before and after ringing. They're trying to remove what's called pre-ringing, so that ringing that happens up front, and use a filter that actually only has a bit of post-ringing. The theory being, as I understand it, that post-ringing can kind of be concealed within the sound. What Rob's saying is use the two of them to reconstruct the sound effectively, and you don't need to hide any of it at all. That's my basic understanding of it. But as I said, this gets really technical, so strap in and hold on and take from it what you can. I hope you find it useful as Rob continues this conversation.
What I realized was that if you didn't use a Sinc function, then your reconstruction of transient information would be severely hindered and altered. And what would happen would be that transients would be, when it goes to the interpolation filter, would either be slightly too early or slightly too late. and they will constantly modulate backwards and forwards. And that modulation would depend upon the design of your filter, the music that's happening in the future, and the music that's happened in the past, because they all have an effect on your transient reconstruction.
The slide that you can see on screen is a slide that's actually from one of Rob's presentations explaining his DAC technologies. And the reason I've shared it here is that, and what you can see as you look at the slide, is that the top sine wave coming in is how the original signal could have been received. The bottom red trace is how the DAC has tried to interpret it using a series of samples. And you can see here, when you look at this, the samples are a little bit behind the actual process of the sine wave. So it's like they're ramping up rather than coming straight in with an accurate representation of that sine wave. So that's what they're trying to reconstruct with either interpolation filters or Rob's specific WTA filters.
The only way of eliminating that issue is to use a Sinc function. So I thought, okay, we've got 16-bit digital data. How can we reconstruct this so that it's 16-bit accurate, so that we get the waveform to 16-bit accurate? And that, when you do the sums on the back of an envelope, you come up with something like more than 500,000 taps, 750,000 taps. This is 1980.
Yeah, wow.
When CD hadn't been invented, DSBs hadn't been invented, FPGAs hadn't been invented. When I went to university, we were programming our mainframe computers with punch cards. And I'd done some work in the vacations on an oil rig computer, and designed an oil rig computer using a newfangled device called a microprocessor. And that device, with 8 bits, had 2K's worth of memory on board. And it was a state-of-the-art device. The idea of using 750,000 taps on a Sinc function, that was just completely impossible, and it would never be fixed. So to me, that was the reason why the original vinyl recordings sounded so awful. And I wasn't entirely right about that, because there were other reasons why digital sounded bad. Half of it was down to the interpolation filter, and half of it was down to the DAC issues, the HD issues, those kind of things. But it was a fundamental flaw of digital audio that it couldn't reproduce transients accurately and properly enough. One of the big problems that we have with interpolation filters is that the industry is hooked on this idea of ringing of filters as a bad thing. And a Sinc function will ring for an infinite period of time. So therefore, a Sinc function is seen by the industry as being something that you should not do, because it rings and rings and rings.
Okay.
The industry, and that includes MQA, have got this completely wrong.
Another slide that Rob provided me in his presentation pack is the one that I'm showing on screen now. And what it's demonstrating is that the interpolation filters that are used in other products, and indeed, according to Rob, what's used in MQA, will produce a sine wave, and you can see in the top sine wave there, that it will produce a sine wave that ramps up, similar to the way we looked at in that previous signal where the digital sample missed the beginning of the sine wave a little bit. So I didn't interrogate Rob too deeply on this one. Obviously everyone's going to have their different opinions on what's good and what's bad, and I'd need to talk to an MQA expert to get the full picture here. But as I understand it, what Rob's suggesting here is that any filter that's not using the Sinc function that he uses is therefore going to be unable to correctly reconstruct all of the timing information in the signal. That doesn't mean it's going to be a dreadful sound overall, it just means the transients are not going to be as sharp and clean as they could be. And in my experience of listening to the Chord Q test, there is definitely something in what Rob's saying here. So the quality and the focus and the clarity of the instruments and the placement, because of those transients being a little bit cleaner and a little bit sharper, is noticeable. It's not black and white compared to other manufacturers in my experience, but it's definitely something that does seem to provide some fine detail improvements. Rob's going to go on now and explain why, in his theory, MQA and other manufacturers have it wrong. But again, I just want to state, and I said this in video 1, that this is one person's opinion, one extremely experienced and knowledgeable and intelligent person's opinion, so it's definitely very valuable. I'm sure that someone who's an MQA supporter will have their own arguments as to why that approach is better. Likewise, anyone using their own interpolation filters that are not the WTA filters using the Sinc function will have their own reasons for doing that. So I definitely believe there's a lot of merit and a lot of validity in how Rob's design works. But at the same time, I'm not endorsing this as the one and only approach. I don't know enough to say that. It's all just a part of the information puzzle that we need to be able to make informed decisions when we're buying products.
And the reason they've got it completely wrong is that sampling theory requires that your signal to be bandwidth limited. So it can go up to 22.04 kilohertz, and at 22.05 kilohertz, it has to be zero. That's what you mean by bandwidth limiting.
Yep.
But when you use an impulse, your energy at 22.05 kilohertz is exactly the same as the energy at DC, because it's not bandwidth limited. And when you put a bandwidth limited impulse into a sinc function, it just does not ring at all. It will reconstruct the original signal completely perfectly. There'll be no extra ringing. If you put a bandwidth limited impulse response into an MQA filter or a minimum phase filter, which is what all these high-end companies use, it will ring. It will ring more than it should do. It's only a sinc function with a bandwidth limited signal, which is what you're supposed to use for digital, that won't ring.
Just a quick comment here that I find this absolutely fascinating, that there are such differing opinions on something like digital audio, where so much of digital is defined by the maths, and yet there are obviously multiple different approaches. There are people who 100% support MQA in their DACs. There are people like Shit Audio who to this day are not supporting MQA in their DACs and obviously have good reasons for it. And I only use Shit as an example there because I've seen some interviews of them where they've said they're not supporting it at this time. So there are multiple camps here going on, where you've got Rob focusing on Sinc Functions in his WTA filters. You've got MQA supporters focusing on the MQA filtering. And finally, you've got those who are using their own interpolation filters that aren't using Sinc Functions. So that's minimum and linear phase type filters, if you've seen those on DACs that you've used before. All of these companies and the engineers behind them are using different approaches to decoding a mathematical and defined process. And I find it very interesting that there isn't consensus on the best way to do that. So one of the things I was really curious about, and the reason I did this slide, was in trying to understand, and correct me if I'm off track here at all, my understanding from our first conversation and continuing now is that the WTA filters, when faced with something like this set of samples here, their job is to reproduce this waveform.
Yeah.
There.
What they're trying to do is to reconstruct the bits in the middle. So your green dots are perfectly on the white line. It's the bits in the middle that aren't. And if you look at a NOS filter, then you convert your green dots into straight lines. And that is a first order whole interpolation filter, which is a very crude interpolation filter. And you get a huge error because it's nothing like the original white line. When you run a full output transient signal, you end up with huge errors. If you put a simple 20 kilohertz burst, for example, and set things up in a particular way, you'll get it so that the first pulse is completely lost. So it's accurate to within 1 bit. And so you've missed the whole data sample. So we're talking about very, very large amplitude errors here when you're reconstructing transients. So when you're talking about sampling, don't think of it in terms of small signals. That's another issue. If your transient is halfway in between, it crosses through zero halfway in between.
Yep.
When you look at a real DAC, it won't do it halfway. It will do it either slightly too early or slightly too late.
Right.
And what's key is that this timing error is constantly churning around. It's constantly varying. And that variation gives the brain huge problems. Because it can't get to grips with the audio signal, can't make sense of the audio signal. And then your timbre variation gets degraded, your soundstage gets degraded, the perception of bass gets degraded. And these are all things that you hear when you increase the tap length and make it more sync accurate. So, for example, when you're looking at the Q test, you're looking at, now what's the Q test? The Q test is 48,000 taps. That's about 12-bit accurate or thereabouts. So it's the same as synced 12 bits. So you're going to get your reconstruction to 12-bit accuracy. When you plug an M scaler in, then you've got your full million taps. They are the coefficients are identical to Sinc to 16.7 bits.
Mm-hmm.
So it's exactly the same as Sinc to 16.7 bits. So we're reconstructing our waveforms to guarantee better than 16.7 bit accuracy.
Okay. Yep.
The beauty of 16 bits is that if you could argue that if you've got a 16-bit reg book, then you'd only need to reconstruct your timing to an accuracy of 16 bits because it's 16 bits sourced. That's not quite true, but you could make that argument. This doesn't mean that we've got a 16.7-bit accuracy DAC. That's not what I'm talking about. Because if you put a sine wave in, put a regular sine wave into any interpolation filter, 24-bit sine wave in, you're going to get 24-bit coming out because there are no transients involved in the sine wave.
Yeah, okay.
And all our measurements that we do, none of them have transients because they're just simple steady-state signals. Only when you're talking about transients that this issue of the accuracy and how you reconstruct the original transient becomes important.
Yep.
A lot of people say, well, if your filter's only 16.16-bit accurate, then you're only got 16 bits coming out on your sine wave, and that's not the case. It's still...
What I've taken away from this, though, is that the filters are not trying to recreate something that's not there so much as position correctly where it belongs in the signal.
Exactly.
Okay.
You're not creating new information.
Mm.
What you're doing is you're preserving the information state of the original recording. Assuming it was an M-bit output that was accurate enough for you to perceive, and assuming that bandwidth limiting of its own makes no difference to the sound quality, then you were using a Sinc function of the appropriate length. You would perfectly reconstruct everything to the accuracy that you require.
Mm-hmm.
Question is, how accurate do we need that to be?
Yeah.
And that is something you can only do by making it more Sinc-like, making it more Sinc accurate, and doing listening tests. And that's what I've been doing. That's what was driving me on all this, because my first WTA filter only had 1,000 taps. That's going back to 1999 with the DAC 64. And as FPGAs have gotten better and more capable, we've managed to improve the tap length. So now with the M scaler, we're looking at a full 1 million taps. And every time I've increased it, as time has gone by, probably seen a doubling every 2 or 3 years, or a tripling every 2 or 3 years. I've noticed that the timbre variation is better, the instrument separation and focus is better, the bass definition is better, and these are all things that we know that transients are very important to for the brain to perceive. And I'm going to keep going until I can no longer hear a change. Eventually, there will come a time when we can no longer hear a change, in which case that will make me very happy because I don't have to worry about WTA filters anymore. Focus on something else. That's been my driver, constantly improve until we can hear no change.
Great. And so just to clarify my understanding, what I gather is that your DACs are the only DACs that are using a Sinc function filter, in this case, a WTA filter, and others are using an interpolation style filter.
Well, they'll use either a standard interpolation filter, which is based from maths, so it'll be a Kaiser interpolation filter. One of the things that, you could say, why am I not using everything being Sinc, and then when it drops away, it becomes zero? The problem with that approach is that it actually doesn't sound too good, because there's an abrupt change from zero to your Sinc function turning on. So you've got to taper it so that when it starts to disappear to zero, because you have to eventually stop doing your processing, you've got to taper it, and it's how you do that tapering process that's important. The WTA algorithm was driven by a number of different things. My understanding of the maths involved, getting rid of aliasing, image aliasing, which was very important from transients, and fine-tuning and tweaking all the various different parameters that you've got and how you create that taper. I did hundreds and hundreds of different listening tests to try and optimize it. And what I ended up getting was that the best filter to use is probably a Kaiser filter. A Kaiser filter is a nice filter to use as your conventional interpolation filter. And my first listening test, I'd had a 256 tap WTA filter against a 2000 tap Kaiser filter. And the 256 tap WTA filter sounded a lot better than the Kaiser filter.
Okay.
So that gives you at least a 10-fold improvement in transient reconstruction ability. So that's what the benefit the WTA algorithm gives you, that you improve that performance.
That's it for part 3 of the interview with Rob Watts. There's just one part remaining, which is probably going to come after Christmas at this stage. And in that final part, Rob's going to talk about... And in that final part, I asked Rob about why sampling rates matter. If we can only hear less than 20 kilohertz, why does a sampling rate that's well and truly above 44.1 kilohertz, which has been proven to be enough to sample 20 kilohertz effectively? So that's coming up in part 4, along with some other conversation around things like the M scaler versus the Hugo TT2, which one's a better upgrade for somebody looking to take that next step in their audio journey, and a few other bits and pieces of conversation. For now though, I hope that wasn't too overwhelming. I hope you've taken some great information from it, and I look forward to seeing you here next time on Passion for Sound.